I have been working as a data scientist in the US tech industry for the last 10 years. In all these years, I have studied data science in different universities. I have worked in different companies, including Meta, Cisco, and Wells Fargo as a data scientist, and I've worked with hundreds of amazing other data scientists. So in this video, I'm going to share with you, based on my all these years of observation, what the future of data science looks like, and more importantly, what are the skills you should be trying to master in the next 1 to 2 years, so that as the industry changes and evolves, as it always does, you are always ahead of the game. Now, to get a better understanding of where we are going in terms of future, we have to see where we are coming from. If we are coming from this point, then we can see that this is what the trajectory so far has been, and based on that, we can make a prediction that this is the direction we are going to take in future. But if our starting point is somewhere here, then we can see that our trajectory is totally different, and we are going probably in somewhere in this direction. So basically, to give a prediction about the future, we have to look at the history. So let's take a very quick look on how the data science industry has evolved in the last 10 years. And the reason I've picked the last 10 years period is when the industry pivoted from vertical scaling to horizontal scaling. What does it mean? I'll get to that in a minute. And also, this is about the time which I have spent in the industry, and I can share some knowledge with you based on my own observation and experience. So let's go 10 years before, around 2015 timeframe. That is the time when, as I said, we pivoted from vertical scaling to horizontal scaling, and that opened up a lot of opportunities and big breakthroughs in data science and ML industry. Vertical scaling basically means that we were essentially trying to run all our data and compute in a single computer. So for example, this is the big computer we have, and we are trying to run our data and processing it in the same unit. And if we need more compute power or more storage, we just try to make a bigger computer. And that is why we were hearing the terms like supercomputers back then, because we were constrained to run all our processing in a single computer. And even the biggest banks and the biggest governments had access to bigger computers which are not very powerful. Since that was the constraint which pretty much all of us had, it meant that there is only so much compute which we can do in a single computer. And since we were trying to add resources on a single machine again and again, this was called vertical scaling. Around 2014-15 timeframe, we pivoted in the industry from vertical scaling to horizontal scaling. And the basic concept behind horizontal scaling is that you have multiple smaller computers, and then you basically connect all of them through wires, and that is where you process your compute. So now, instead of having one giant computer, you have multiple smaller computers connected together, and then whatever compute you need, you parallelize it through all those smaller computers which are connected together. So this is called horizontal, because we are not now constrained to use a single machine, we can use multiple machines. Now, the reason we saw that pivot around 2014-15 timeframe from vertical scaling to horizontal scaling was that there were two main prerequisites which were needed for us to able to successfully run most of the processing in a horizontal manner. First, we needed bigger bandwidth, so that as we have a lot of data between different machines, these machines can transmit the data in between and can still run intensive data processing. The second constraint was that we need sophisticated algorithms which has the capability of parallelizing the process which we are trying to run on these computers. And MapReduce was essentially the first thing which was introduced, which helped us parallelize most of the processing thing which we were trying to do. Now, to give a very basic understanding of how does MapReduce work, it basically said that, let's say if we had these three computers connected together through wires, and then we have our user here, and this user, for example, wants to know that what is the average value of the data which is stored in all these three devices. And let's say this is the data which is stored in all these three computers, The way MapReduce works is that if we want to understand, for example, average, there is an underlying MapReduce algorithm built in, which will go to all these three computers. It will try to get, okay, what is the count of all the data which is stored in this machine, and then what is the total sum of it. And it will get this from here and from here as well. And once it has all the count and sum from all these three different machines, then it can get that together, and then it can sum up all the data and then divide it by the total count. And this is how, even when the data is stored in different machines, using MapReduce, we can get it processed in a parallelized manner. And the reason it was called MapReduce, because it has two stages. So the first step, where we are trying to get the count and sum, this is the stage of map. And the second stage, where we are aggregating the results, this is the stage of reducing. And this is why this algorithm was called MapReduce. And this was one of the first steps which we needed to be able to parallelize our processing across different machines. Now, when that transition happened, that we were able to successfully transition from vertical scaling to horizontal scaling, it opened up a lot of opportunities in terms of data processing, in terms of running different sophisticated machine learning algorithms, because now we were not constrained by having a single machine's resources. We can just add in more and more smaller, cheaper devices, and we can even analyze terabytes of data without much problem. So around 2015-16 timeframe, we saw that a lot of companies started having their own data centers within their own premises, where they will have a lot of machines and they'll just connect them through wires. And that is where we will try to run our different algorithms. So the way it was working is that, let's say this is my team and I want to run some processing power. I will get some data center. So let's say this is the data center. It has some data and it has some compute power available, and my team will basically connect with this and have our processing run in a parallelized distributed way. I vividly remember that our team used to have its own data center in the door right next to where we used to sit. We had a bunch of machines, they were connected through wires, and that is where we were running most of our processing. And if there is another team which wants to run the processing, instead of spinning up their own data center, they would start sharing a centralized data center, so that a company do not have to maintain and manage different data center. They can just have one bigger data center which is easier to manage, and then different teams throughout the company can start using the same data center. So let's say there is another team in the same company, and if they want some compute power, then they can share the same data center. And for bigger companies, this data center started becoming bigger and bigger, because for bigger companies like Google, Amazon, Microsoft, they had thousands of employees running very data intensive applications. So of course they needed very big centralized data centers. But the problem was that these data centers are very costly to maintain, and secondly, not the entire data center is used pretty much all the time. Now, even if you have 1,000 machines, on average, you would be using about 20 to 30% of that. So bigger companies started having this idea that instead of sharing our data center just within the teams within the company, we can share these data centers with other companies as well. This is a very win-win situation, because bigger companies can rent out their unused resources, and the other companies can rent those resources without having a headache of managing a data center. So this is where the emergence of cloud came in. And companies like AWS, GCP, and Microsoft Azure started penetrating the industry, and more companies started going towards that. And when a lot of companies were using the same data centers, what these cloud providers saw is that there is a lot of duplication in terms of what these companies are trying to do. For example, a lot of companies were trying to install their own database systems. A lot of companies were trying to implement their own content delivery networks. And the companies like AWS saw this as an opportunity. So they say, if you want a relational database, we'll give you that as a service. If you want to implement CDN in your data center, we'll give you this as a service. And the same was true for a lot of data science related work. And we saw an emergence of tools like AutoML, SageMaker, where these cloud services were basically saying, if you want to implement machine learning pipeline, you do not need to have a data scientist. We'll just provide you a UI tool. You can pick which table you want to run this prediction system on, what are the columns you need as an input, what is the thing you're trying to predict, and we'll just run everything behind the scene without you needing to hire different data scientists and machine learning engineers. And this is basically what services like AutoML and SageMaker try to do. And we saw that these services started becoming more mature and more powerful with the passage of time. Initially, it just used to run in a tabular data. Then they said, if you want to run it on a text data, they started introducing services like AWS Comprehend. And finally, it came to a stage where they say, we do not even need your data to train these machine learning models, because we have trained our algorithms on all the data we possibly can get in the world. And they started services like OpenAI ChatGPT or Google Gemini, which is trained on very giant data sets, and then you can just use our services and pay us for that. And this is where we currently stand. Admittedly, the performance of these models, which are trained on some open source giant data set, is pretty impressive, and they can come in handy. And companies are realizing that they do not need very sophisticated data scientists and machine learning engineers, because all you need to know is how do you query these services, for example, OpenAI or Google Gemini, and then how do you craft a good prompt so that it can help you get the answers or predictions which you're trying to do. And if you want to get prediction specific to your data, no problem. They introduced the concept of few-shot learning. A very simple explanation of few-shot learning is that, let's say if this is the bigger LLM, be it ChatGPT or any alternative, and this is an engineer which is trying to make a prediction based off some data. For example, if you are trying to classify if a review is positive, neutral, or negative, then instead of giving a raw prompt, you can basically add few examples in the prompt so that LLM can understand what do you mean when you say positive sentiment and what do you mean when you say negative or neutral sentiment. So these few examples are basically what few-shot learning is, and then your LLM response would be much more intelligent than what it would have been if you just ask it without any examples. And this goes even further. For example, if you're trying to ask an LLM to answer a question based on a company knowledge base, then there are RAG pipelines which could go look into this data based on the question which is asked, and then it will get some very relevant examples and chunks of text from this knowledge base so that LLM can look into that sample text and can get the answer from your material. And if you want to make a prediction based on your tabular data, then these LLMs can actually write the SQL code for you as well, so that you only fetch the relevant data from your tables and make the prediction on top of that. And the best part is that all you need to know is some basic Python and some prompt engineering to be able to do it successfully. Now, this is where we currently stand. And we can see that we have made a lot of progress in the last 10-12 years. And the pattern, you can see that at every stage we make some progress. That progress introduces some challenges. And when we try to overcome those challenges, that is how we make progress. Now, to understand where we are going in future, let's understand what are the problems of today. As you can see, we have made some very good progress in terms of the ease of use and the overall performance of these machine learning algorithms. But the challenges of today's world are also very huge. The first issue is that of data privacy. A lot of these enterprise LLM models, for example, ChatGPT or Google Gemini, when you try to use them and send some data through RAG pipelines or for few-shot learning, that data, which is companies' data, a lot of times sensitive data, is being transmitted to their servers. And that is a big problem for a lot of companies. Companies are very sensitive in terms of with whom these data is shared. And since the data you send to these LLMs actually get used to further train these LLMs, this is a big data privacy problem which a lot of companies are very concerned about. That is why in a lot of bigger companies, including the company I'm working in, do not allow us to use any enterprise LLM where the company's data, even if it is some examples, is being sent to some other company servers. So that is the first problem. The second problem is that though we have these big giant LLMs which are able to answer pretty much any question you ask them, if you try to use them to solve some complex problem, you have to pass in some prompt. And as you see the performance of the model not there, you keep introducing new changes to the same prompt, and before you know it, your prompt is like very big script and set of instructions which you are trying to give to the LLM. And what happens as a result of that is that your LLM does not fully get the instructions, and you start seeing big problems in the performance of the model. For example, if you are trying to train LLM to write a SQL code for you to run some data based on the question which is asked. Now, initially you can just ask it, okay, write the SQL code, this is the tables I have, and it will give you a very decent performance. But then as you evaluate the performance, you'll see that the model is making some problem here and then there. And then in order to tweak that, the only lever you have is that you add more instructions to your prompt, which has all the nuances of if this happens, then do this, if this happens, then do this, and then you have some example code, etc. And this leads to the LLM getting a little confused, and you see a big drop in performance. And since these LLMs are sort of black boxes which you're trying to deal with, there is no way you can further optimize their performance. And the third issue is that of cost, because every query to these LLMs, that is costly. And when these bigger companies are trying to use these LLMs pretty much for every use case they are trying to handle, you can see that this cost is going to go astronomically high if we fully embrace AI in all the aspects of the company. So these are the three problems of today. First is data privacy. Second is that the prompt gets bigger, the performance goes down. And the third is that of cost. And companies are thinking, how can we solve these problems? And how we solve this problem is going to define the future, where we are going in 1 year, 2 years, 3 years down the line. Now, my prediction of the future is that instead of using these enterprise LLMs, which are hosted in some other company servers, and you have to send your own data to get some information out of it, which incurs some cost, I think go away from that to a world where we will have smaller LLMs in companies' owned cloud instances, and these will be much smaller open source LLMs which will be fine-tuned and optimized to do some specific task. So think of the current LLMs as big giant encyclopedia which can answer pretty much any question you can ask it about any domain. We are going to go away from that to smaller encyclopedias, one specifically fine-tuned and specialized, for example, on how finance work in Wall Street. So then our workflows will consist of these smaller LLMs working with each other to help us solve bigger complicated problems. And this is what is currently known as LLM agentic framework. So going back to the example which I was trying to give to highlight the problem of having one giant LLM, which is if you try to ask it to create a SQL based on the natural language prompt to get the right data from the tables, the prompt starts getting bigger because it is just one LLM trying to do the task for you. In the future world, when we'll have these agentic frameworks with smaller, more specialized LLMs, the task will become a simple step-by-step process to be executed by different LLMs. For example, the first LLM will just look at the query and try to see what are the tables we need to query for that. And that's it. It will just be specialized for that particular task. For example, if your query is what is the average spend by customers who are age 18 to 20, then the first LLM will just go and figure out I need to query the table which has users demographic information, for example age, and I need to fetch the table which has customer spend information. And these are the two tables which are needed to answer that question. So let's say this is that first LLM. Its task is to find tables. So once it has figured out what tables it needs, then it will pass on its information to the second LLM. And the task of the second LLM would then just be what the SQL query should be to get that information. So this will write the SQL. And once it has written the SQL, the third LLM would just then check the results. And if it thinks that this is a good query, it will pass on that for the final output. Otherwise, it will send it back to the previous LLM with its feedback so that it can make improvement into the model. And this is a very simple example with just 3 LLMs. And there could be scenarios where you have hundreds of these agents working in a system to help solve a complex task. And the reason this is very elegant solution is that first, because these are smaller LLMs, they are much cheaper and they can be hosted in your own server, which means there is no additional cost to it and there are no data privacy issues because your data is not going somewhere else. Second is that because you have these different LLMs talking with each other, you can improve the performance of each of these individual components and fine-tune them so that if the end result is not looking good, you can trace it back to see which specific LLM agent made the mistake, what mistake did they make, and then you can further fine-tune them. You can improve their prompt so that they do not make those mistakes again. And since these are smaller LLMs, the cost to host them and run them is also much lower as compared to using some giant LLMs which are hosted on some third-party server where every request you make and every result you get costs you money. With the passage of time, these LLMs, they will become even more powerful than what they currently are. And also, because of Moore's law, the computational power will also become cheaper and our servers will be much more powerful. And when you add these two facts together, it means that even our smaller LLMs will be much more powerful and able to solve. And when you connect a lot of them together, they'll be able to solve very complex problems with much greater efficiency. So this is where I think the future of data science and machine learning lies, in agentic frameworks where we have smaller, specialized micro LLMs working with each other to help solve complex business problems. Now, going back to the very original question, that what are the skills you need to learn today in 2025 and 2026 so that when these agentic frameworks come to full boom in next 1 to 2 years, you are fully ready and equipped to master these. I think the very first fundamental skill which you have to be very proficient in is that of Python. In the last 10 years, Python has pretty much established a monopoly in terms of being the language which all data scientists, all machine learning engineers are using on a day-to-day basis, and all the relevant technology is having essential support for this programming language. It is also very easy to learn and a programming language of choice for a lot of software engineers. So Python is going to stay there at least for the next 5 years. And if you want to be a good data scientist or machine learning engineer, this is one skill you definitely need to have. Because Python is what you'll use to write these agentic frameworks, to making these queries, to help them make these bigger systems of micro LLMs. The second skill which you should definitely help prioritize learning is that of cloud services. Pretty much every company currently uses either AWS, GCP, or Microsoft Azure. You do not have to learn and master all of them, just learn any one, and a lot of knowledge translates equally to the other services as well. And the reason it is going to be even more important in future is that a lot of these agentic frameworks, they will be hosted on these cloud platforms. So how do you run and manage instances? How do you have proper security permissions? How do you retrieve data from different kind of cloud services? You need to have a good understanding of that. So Python is the first one. Second is cloud services. The third thing which you need to know is that evaluation and performance monitoring of these agentic frameworks is not very simple and straightforward, because it is not a single system which is giving you the output. Your system now consists of different, sometimes dozens, even hundreds of smaller LLM agents. So defining a system of how do you evaluate, test, and optimize the performance of these systems, this is going to be a domain which will not be very straightforward and which you should definitely start prioritizing learning as well. And the fourth thing is having the fundamental ML knowledge, so that you not only know what is at the surface, but can also see that how the technology has evolved from the fundamental machine learning algorithms to transformers to GPTs to now this agentic frameworks. So having some understanding of this lineage and this historical evolution is very essential, and that is the factor which would be differentiating from people who are working at just the final output layer versus who have a very good understanding of the theoretical underpinning of these systems as well. And finally, I would say the premise of this video was where we are going in future. If you are applying for data science jobs right now, these are not the skills which gets asked in today's job market. So if you are trying to get your first or second data science job, then focus probably on what gets asked in the interviews currently first, so that you could get your foot in the door. And once you get your first job as a data scientist, then you can start thinking about what are these latest and greatest innovations out there in terms of data science and machine learning, and how you can embrace them and start using them in your day-to-day work, so that you are always ahead of the learning curve. And when these future technologies come to maturity, you're already way ahead of the competition because you already have 1 to 2 years of experience working with them. But if your current priority is to get your first data science job, then don't spend too much time on it. Try to understand and learn what gets asked currently in the data science job market. I've created a free guide on that, on what are the materials and topics you can go through for that. The link for that is in the description. And I've also created a video on the topic of what are the 4 books which you can read, which will help you answer at least 90% of the questions which are asked in most data science interviews. The link for that video is somewhere here. Please check it out. I'm pretty sure you like it. Thank you so much for watching.